It is a pleasure to have you here today. We are going to continue sketching curves, but today we're going to formalize things a little bit. We're going to have an explicit list of things that we want to put in our graphs. And so let's take a look at the first half of that list. These are just the first few bits. We're going to have a few more afterwards, but anytime we want to sketch the graph of a function, there are certain things we want to look at and make sure that we are representing accurately in the graph. The first thing we should check is the domain of the function. All right, we shouldn't be graphing a function without thinking about what the domain is going to be. That's an important part of what a function is going to look like. Once we figured out the domain, we should figure out the intercepts. The y-intercept is always really easy. We just plug in x equals 0 into the function. That tells us where the curve will intersect the y-axis. And then to find the x-intercept, we set y equal to 0, or we set the function value equal to 0, and we solve for x. Now, oftentimes in a calculus class, you're going to be given functions where it's pretty easy to find the intercepts. It's pretty easy to solve f of x equals 0. That's not always going to be the case. There might be examples in your class where you cannot do that because it's just a complicated equation, right? If it's a polynomial, we often know how to solve those equations, but if it's got a polynomial and some logarithms in it, we might not be able to easily find the roots exactly. And so if it's particularly difficult, we can skip that step. But if it's something where it's easy, we definitely want to find those intercepts so that when we're graphing things, we can make sure that the intercepts are represented accurately. All right, the third step is optional but useful. We should check and see if the function has any sort of symmetry. Even functions are functions where f of negative x is equal to f of x for all x in the domain. If that's the case, the function is even, and that means that the graph is symmetric about the y-axis. And that cuts our work in half. We only have to look at one side, and then automatically we get a reflection on the other side. Similarly, if we have an odd function where f of negative x is equal to negative f of x for all x in the domain, the function is odd, and if this is the case, the graph is symmetric about the origin, meaning we can rotate it 180 degrees about the origin and get the same thing. And that again cuts our work in half because we only have to do half of it, and then we can rotate that 180 degrees around the origin. And then the third example comes up mostly in trigonometric functions. If we have a periodic function, then we only have to look at one length of the graph that has the same length as the period, and then we can translate that over and over again and again to figure out what the rest of the graph looks like. There aren't many functions that are periodic, so this isn't going to be something that comes up that often, but if you're graphing something like sine of x plus cosine of x, you know that that is a periodic function, and you can use that to your advantage. Okay, now the fourth example is asymptotes. We have seen some examples with asymptotes, but we're going to end up seeing more examples with more asymptotes sometime in the next several examples. And so we want to make sure that if there are any asymptotes, we are graphing those correctly. Now, we will have a horizontal asymptote if the limit of the function as x approaches infinity or negative infinity is some constant number. If that's the case, then the line y equals that constant is a horizontal asymptote, and we should make sure that that is a part of our graph. We often see horizontal asymptotes when we have rational functions, so that is one place where we definitely want to be on the lookout for them. Also, exponential functions can have horizontal asymptotes, right? E to the x, 3 to the x, etc. So those are also situations where we might have horizontal asymptotes. And then also, we might have vertical asymptotes. The line x equals a is a vertical asymptote if the limit as x approaches a, either the overall limit or the limit from the left or the limit from the right is equal to positive or negative infinity. This will often happen with rational functions. It might happen with logarithmic functions. Also, the tangent function has vertical asymptotes, so we want to be on the lookout for those because we want to make sure that we are including those accurately in our graphs. For rational functions, it's not that difficult. We locate the vertical asymptotes by setting the denominator equal to 0 after canceling any common factors. We also could have slant asymptotes. I haven't listed that here, but we have seen with some rational functions, we have slant asymptotes. That is also something that we would want to include in our graph. All right, this is the first half of the items. Let's look at the second half. Pew! All right. We have intervals of increase or decrease. We've been looking at these a lot lately. We can use the first derivative and then a sign chart to determine the intervals on which the function is increasing or decreasing. And then that will also give us our local maximum and minimum values. Remember that we want these to be accurate on the graph because these are often really important points on the graph. They're important function values. If we're looking at something that's being thrown in the air, we might want to know its maximum height. If we're looking at a profit function, we might want to know the maximum. These are important points, so we really want to make sure that we're representing them accurately on our graph. Along with that, we have concavity and points of inflection. Those pieces of information come from the second derivative. So we definitely want to take the second derivative and see what that tells us about our graph. And then finally, once we have all that information, we want to sketch the curve. So we want to sketch the asymptotes as dashed lines. We want to plot the intercepts, the maximum and minimum points, the inflection points, and then we want to draw the curve so that it passes through those points. It's rising and falling according to the intervals of increase and decrease. The concavity is correct, and we want to make sure that the graph is approaching the asymptotes in the right way. And then at the very end, it says, for additional accuracy, calculate additional points and or derivatives. Sometimes all of that information that we've gotten isn't quite enough to know what's happening to the graph in certain intervals, and so making a very small table of values to get a few points is often very helpful in making sure that our graph is as accurate as it can be. So we've come a very long way from an algebra class where we're graphing things. Usually when we're in an algebra class, we're making tables of values and we don't know where those local minimum and maximums are, so we can't draw them accurately. And we might not know what's happening to the graph in between our points. If we've picked some really good points, it might give us a bit of information about the graph, but we don't actually know what's happening outside of those points. We can only guess. But now that we have calculus and derivatives, we can get all of this important information and draw beautiful graphs, which is exactly what we're going to continue doing.